Parallel transport of vectors. 1. We will discuss the parallel transport of vectors in curved spacetime. This is one of the core concepts in general relativity. The key features of curved space we have seen so far are: the basis vectors change from point to point, and concepts such as covariant and contravariant quantities necessarily emerge. In flat Euclidean space, the basis is the same everywhere, so a vector can be written with the same basis and the same components throughout the entire space. In curved space, however, the basis varies even within a single coordinate system. Let us explore how to express mathematically a vector running through such a space. To understand parallel transport, we must first have a firm grasp of the fundamental properties of curved space. In this chapter, we begin with the basics, the line element and the metric tensor, and build a solid foundation from which we can advance step by step toward the heart of the subject. Since this topic requires considerable time, we will divide it into several parts. Line element ds squared in curved spacetime. In this chapter, we derive the line element in an actual curved space. As a concrete example, let us find the line element of a two-dimensional sphere embedded in three-dimensional Euclidean space. We begin by setting up the physical picture. This surface has only the dimensions of the boundary of a sphere of radius r, a constant, existing in three-dimensional Euclidean space. The interior of the sphere is empty. Think of it as the surface of a soap bubble. While spherical coordinates, r, theta, phi, specify positions in three dimensions, the two-dimensional sphere requires only theta, phi. First, let's review three-dimensional spherical coordinates. Spherical coordinates are represented as r, theta, phi, and their relationship to Cartesian coordinates is given by Since we want to combine everything into a single expression using Einstein's summation convention, we relabel the coordinates x, y, z as z1, z2, z3. In flat space, upper and lower indices represent the same physical quantity. Let's express this in coordinates on the two-dimensional sphere. Since the radius r equals r is constant, we set These are the coordinates yn expressed in terms of the two-dimensional sphere's coordinate values. Although there are three equations, there are only two parameters, theta, phi, so this is a two-dimensional space. Let us denote the intrinsic coordinates on the sphere as theta, phi equals x1, x2. Since each point on the sphere exists in three-dimensional Euclidean space, taking the total differential allows us to transform to the intrinsic coordinates on the two-dimensional Riemannian sphere. The total differential shows how infinitesimal changes on the sphere correspond to those in three-dimensional space, from which we can derive the metric of the curved space. Using Einstein's summation convention, this becomes Here, n is the index for three-dimensional space, so n equals 1, 2, 3. And mu is the index for coordinates on the two-dimensional sphere, so mu equals 1, 2. Next, let's find the line element of the two-dimensional sphere. In three-dimensional Euclidean space, the line element is expressed as Writing this in matrix form. We substitute the total differential obtained earlier into this. Since this matrix expression represents the line element ds squared, the product of the partial derivative matrices, excluding the infinitesimal displacements dx1 and dx2, gives the expression for the metric g mu nu. Let us expand the metric matrix and derive the explicit form of this expression. The product of the partial derivative matrices becomes the metric tensor. We expand the metric matrix. In what follows, we will explicitly compute the line element of the two-dimensional sphere. This is the metric tensor for the two-dimensional Riemannian sphere. Let's actually calculate it. Please pause to check the calculation. We have derived the metric of the two-dimensional Riemannian sphere. Therefore, the line element is This is the line element on the two-dimensional Riemannian sphere. Why is the metric g mu nu equals partial yn over partial x mu partial yn partial x nu? We derived this by taking the line element of flat n-dimensional space and transferring it to the coordinates mu, nu of a curved space. In other words, we applied the chain rule to transition from Cartesian coordinates, n, to the curved surface mu, nu via an intermediate step. The coordinate transformation law for the covariant metric tensor was by definition, g mu nu is the inner product of the covariant basis vectors. Since flat n-dimensional space has an orthonormal basis, A alpha becomes E alpha and A beta becomes E beta, here, G alpha beta equals E alpha dot E beta. Let us confirm the physical meaning of partial x alpha over partial x prime mu and E alpha. Regarding E alpha, if we denote the unit vectors, orthonormal basis, in three-dimensional Cartesian coordinates as E1, E2, E3, then the position vector r pointing to any point in space can be written as using Einstein summation convention. In Cartesian coordinates, raising and lowering indices makes no difference. However, we use the mixed form to apply Einstein summation convention. The inner product of the basis vectors gives the Kronecker delta. The basis vector A, prime mu of the two-dimensional sphere is obtained by differentiating the position vector, r with respect to x prime mu. This is expanded via the chain rule using the Cartesian coordinates yn as intermediate variables. Since partial or over partial yn equals en, the expression becomes the inner product, metric, of the orthonormal basis in Euclidean space is given by in Euclidean space, gnm equals e n dot e m equals delta nm, giving 1 when n equals m and 0 when n not equal m. While partial yn over partial x prime mu strictly represents the coordinate index of the components of the basis A prime mu, passing through the orthonormal basis reveals the hidden Kronecker delta, making this expression one that represents the basis itself. This partial derivative acts as the transformation from flat Euclidean coordinates, n, to curved space coordinates mu, nu. This product of partial derivatives represents the metric of curved space. Combined with the components, a vector at point x in curved space can be written as this vector lies on the tangent plane at point x on the surface. In the next part, we will tackle parallel transport itself.